To graduate? Well, I'm in May. Oh, nice. Now you've been December though. Okay. Little Caesars. I felt tired of meeting earlier. Walking through someone's here. Someone's sitting there. Someone's sitting there. You trying to sit here. Okay, Lauren, did you hear that? It'll probably be Little Caesars because Connor said something about being on the phone with them all day. You should. Service right now. Cool.
So yeah, what are you doing all the way up there? Huh? What are you doing all the way up there?
I'm hosting today. All right, everybody, welcome to Math Club. There's pizza and beverages in the back, so please feel free to help yourself to that. But for our speaker today, we have Emily Sundberg, who will be talking to us about her experience with the Math REU and some zero knowledge group. So please welcome Emily.
Hi everyone, like you mentioned, my name is Emily Sundberg. I'm a senior math major here at Clemson, and I'm really excited to tell you guys a little bit about my experience this summer in an REU and a little bit about the research that came out of it relating to zero knowledge. So a little bit about what we're going to go over today. Some of our topics are: what is an REU? What does it look like? How do you apply? We're going to talk about a few definitions. They're pretty loose, nothing too scary. Interactive protocols, the discrete logarithm assumption. Then we're going to go into the fun part, which is what is zero knowledge. And then we're going to talk about matrix products and matrix folding, which was the bulk of our research here this summer. And then I'm going to go over a few applications of zero knowledge in the real world. So to start,
I have to click on the slide.
So what is an REU? REU stands for Research Experience for Undergrads. And it's a really cool opportunity to conduct unique research in a small group or individually. The size of the groups really vary a lot. My group was 4 people total, 4 undergrads total, but some are more, some are less, some are simply just individuals. It really is just a range, and you can also, it also breaks up into smaller groups as well. So we had a couple people working on a coding implementation project, but like I was not part of that. So sometimes we broke up into even smaller groups. It's also a great opportunity to get a feel for research in a non-committal setting. At this point, you're an undergrad, so you're not in grad school yet. So it's a great opportunity to just kind of test it out and see how you feel, how you like it. It's also a good opportunity to learn about a new topic. So we learned about zero knowledge, which is a really exciting field, and it's really current. So that was really exciting for us, and it's usually something that you haven't heard before. So that's just a really exciting opportunity. Most of them are paid with a stipend, so it's really nice. It's kind of like an internship. You get paid for it most of the time. On applications, they would tell you if you're getting paid or not. But those are funded by grants from the National Science Foundation or the NSA, or just another grant that the program gets funded through. It looks really great on grad school applications. It's a great resume builder. Some undergraduate research just always looks great on your resume. So it's a great opportunity to look good there. And then a lot of schools will have REUs in different topics. So like I did a math one. They also do chemistry, physics, material sciences, and things like that. So it's not just limited to math. I know here at Clemson over the summer, we had all of these different topics. So it wasn't just us. And then my situation was not unique, but like kind of unique. I did my REU here as a Clemson student. That's not necessarily the norm. A lot of people will go to other universities and do it. Every other person in the program with me was from a different university. So it's not necessarily how it has to go. And then I just kind of wanted to walk through a day in the life. So we were provided housing on campus at Thornhill Village. We had 4 people, 2 girls and 2 guys. So we had a little duplex. So we could just all hang out together in one area. We'd walk over to Harris Martin at like 9 a.m. Most of us woke up at about 8:40, so we would pack a breakfast and then eat it once we got here. Usually in the mornings, we would eat our breakfast and kind of go over a little bit about what we wanted to do in the day. We would talk about, what we wanted to get accomplished, or check our emails and just, get ready to begin. And then we start working on our projects. We might throw a problem on the board. We were up in 202, I think, just upstairs, pretty much all summer. And then in the middle of the day, we would take lunch. Took about an hour. It was pretty flexible though. Sometimes we would bring a lunch. Sometimes we would go to like an on-campus location. Some REU programs will provide you with a meal plan. Others, like our program, gave us a meal stipend. So it depends on the program that you go to. And then also sometimes one of our mentors, Marvin, who's a PhD student, I think he's on the Zoom, he would treat us to lunch occasionally, and that was very nice. So shout out to him. And then our afternoons were mostly spent talking to our mentors. We would present what we had found and what we had questions about. And that was most of our afternoons were spent doing. We leave around 5, sometimes earlier, sometimes later. Presentation days were always fun because we would usually leave early on presentation days. And then in the evenings, we would hang out. Sometimes we did game nights. We went to the movies once. Sometimes we would work on the project. Sometimes we would do some reading. It depends, but it's fun. You just get to, hang out with some new people. And then definitely sleep. Lots of sleeping was happening. So how do you apply to an REU? This website, mathprograms.org, is really helpful. It's very convenient and has almost all of the REUs listed on there. You can apply to pretty much all of them right there. If you just go to view programs and then click on or search REUs. Pretty much what you'll need, at least for the math REUs that I applied to, some different ones might need different things, but for math, you really need your transcript, a CV or resume, 2 letters of recommendation. Some require 1, but most require 2. And then a letter or a personal statement. And then math program is really convenient because it'll keep all of your information right there. You should definitely tailor your applications to each individual school that you're applying to, but the stuff like your transcript, you can keep that and just keep submitting the same document. It'll just stay right on there. And then your letters of recommendation will also stay there, so you only have to send an email to your letter writers once and keep reading the same ones. So it's very convenient. REUs are pretty competitive, so I do recommend starting the process really early. The applications close in mid-February. I started very late January, beginning of February, and there were some opportunities already closed to me. So I definitely recommend starting a little bit earlier than that, just to not miss out on any opportunities. But like in the late December, mid-January timeline is what I would recommend if I were to do it again. And then some REUs do have specific applications on their websites. So if there's a certain school that you're interested in and you don't see it on the math program's website, you can look it up. Or I'm pretty sure if you just Google math REUs, there's a Google site that has like a lot of them listed, even the non-math programs one with their corresponding applications. These were some B-rolls I took over the summer, just, some fun examples of what we did. This was a game night. We got our butts whooped at Clue by a different grad student, Michelle, who whooped us in Clue. That was embarrassing. And then that was just a picture of us walking back from Thornhill. Those were all of the other people who participated in the program with me. So yeah. Are there any questions about the REU specifically before I move in to talk about the math or anything like that? Okay. If anything else comes up, feel free to stop me. Okay, so we're going to start with some loose definitions. These are pretty loose and pretty much just what we need for our purposes. So for a group is a set with one operation, usually multiplication or addition, and the corresponding inverse property. A field is a set with both addition and multiplication, as well as their inverse properties. The integers are a group because for every integer x, there is a negative x that's also an integer. That's the additive inverse. And then for the integers, they're not a field because they do have the additive property and the inverse property, but they don't have multiplication as well. You only, the multiplicative inverse is 1 over x, but 1 over x is not an integer. So that's just some loose definitions for groups and fields. It's not super necessary for this, but it's just kind of an overall underlying definition that kind of just affects everything a little bit. And then I know the definition of relation just can be very ambiguous in math, but this is how we're going to define it for our purposes in cryptography, specifically zero knowledge protocols. So in this situation, a relation R consists of two elements, S and W, where S and W satisfy a certain set of properties. This is also known as a predicate. And an element of R is considered a statement witness pair. S is the statement and W is the witness, also known as knowledge. So W is that piece of knowledge that someone is claiming that they know. You'll notice also in the pair S and W, they are denoted with a semicolon in between them. That semicolon denotes the separation between what is public and what is private information. So on the left of the semicolon is the S. That statement is fully public. Anyone has access to that statement. That is completely public. But the witness W, that's on the other side of the semicolon, and it is private. No one gets to know that, and unless obviously you tell someone, but for the most part, that is private, and that is kind of what the zero knowledge proofs revolve around. And then we're going to use the relation definition a little bit later. So next I'm going to talk about interactive protocols. So an interactive protocol is a system that demonstrates an exchange between a prover and a verifier. The prover is trying to convince the verifier that a statement is true. Most of the time, this statement is that they know some specific knowledge. So the idea, if I'm the prover and you're the verifier, I claim that I know a piece of information, and you're going to verify that I do in fact know it. There are two main properties of interactive protocols. Those are completeness and soundness. The idea behind completeness is that if the statement is true, the prover will always be able to convince the verifier. And then soundness is that if the statement is false, the prover will never be able to convince the verifier except by an incredibly small possibility. This probability is incredibly small, very unlikely in practical purposes. It's negligible, but of course it's not 100%. But it's very strong. So just kind of a little diagram of an interactive protocol is kind of what I have here. So you have two parties, your prover and your verifier. The prover creates a commitment to their statement and sends that to the verifier. The verifier doesn't believe them, so they're going to send over a challenge. And then the prover is going to do a little math manipulation and send over a response. So what makes this an interactive protocol is the verifier sending over that challenge. So the verifier is actively choosing something to be the challenge. You can make this non-interactive by using a random generator and a hash function to encrypt it. Okay. So next we're going to talk about the discrete log assumption, also known as the decisional Diffie-Hellman assumption. And this is used in a lot of security and privacy protocols right now. This is what a lot of our privacy is based off of, like currently. The idea of it is that we're supposing G and Y are elements of our group with prime order P. P being very large, like P is not like 3 or 4, P is thousands of digits. The idea is that it is computationally hard to find an integer x such that y equals g to the x. Now, when I say computationally hard, I don't mean like you would take your computer a day to run. It would take thousands of years to actually break this, which is not feasible right With the emergence of quantum computers, it could be, but as of now, it's secure. So this is an example of an interactive protocol that uses this discrete log assumption. So similar to the way that the simple diagram was in the last slide, is that you have a commitment, a challenge, and then a response. So the way it works, you can see we use the same kind of notation as with the relation. Both G and Y are public information. And then the X is your witness or knowledge. That is the private information. So only the prover actually knows what X is, and the verifier never finds out. So we're going to choose a random integer T in the group such that G to the T is R. R is our commitment. So we send R to the verifier. And the verifier gets R, says, I don't believe you. So they send over a challenge. Then using the information from the challenge and the T that they chose in the commitment, the prover then computes this Z value and sends it over to the verifier. The verifier receives this. Using the information they have, they can confirm that the prover does in fact know this X, such that our statement holds. If and only if G to the Z is the commitment R times Y to the C challenge. I'm going to go into a little bit about why this math works a little bit later, but for now, this is just kind of an example of how this works with actual math. Okay, so now we get to the fun part. What is zero knowledge? Zero knowledge is really exciting because it's not new per se, but it is very current and it is happening like right now. So the idea behind it is, suppose I have some information. I want to prove to you that I know this information without revealing to you what it is. You never learn anything else about this information other than the fact that I know it. Additionally, I don't want anyone else to be able to know for certain that I do in fact know it. So it's just a two-party verification, like a third party will not be able to confirm. So a zero knowledge proof is an interactive protocol with an extra zero knowledge property. So like before I said, interactive protocols have completeness and soundness. Zero knowledge proofs also have a zero knowledge property that I'll talk about in a minute. Also, it's worth noting that proof and protocol are being used interchangeably in this context. They're pretty much synonymous. It's not like the rigorous proof that we're used to in math. It's basically a protocol or an algorithm. So the Schnorr protocol that I did show you, that is a zero knowledge interactive protocol. So the verifier never finds out what that X value is. So I'm going to demonstrate this through a little example. Thank you. Thanks, Maggie. So we're going to assume, for the sake of this example, that I am colorblind. I went to Five and Below and I bought these two balls. They are identical. I see no difference between these two balls. Jazzy, would you agree with me?
No,
Why not?
they're two different colors.
Oh, really? I don't believe you. I think they look identical. I don't agree. So we're going to set up a zero knowledge interactive protocol to have Jazzy prove to me that these are in fact two different colors. So the way that we're going to do this is, Jazzy, will you please remember which ball is in which hand? Okay, turn around or close your eyes. Okay, I'm either going to switch the balls behind my back or I'm not. But you can turn around. Now, did I switch the balls?
Yes.
Okay, that's correct. Am I convinced yet? No, she could have gotten lucky. She had a 50-50 shot. Let's do it again. Okay, you can turn around. Did I switch the balls this time?
No.
Correct again. I'm starting to maybe get a hunch. Maybe these balls are in fact two different colors. I'm not going to make her do it again and again, but if we were to do this, say 30 times in a row, and she got it correct every single time, I can be pretty convinced that these are in fact two different colors, because the odds of her getting it right 30 times in a row? Basically not. So then, Kyle, I'm gonna ask you a question. If you were to watch this interaction, we're gonna actually assume that you're colorblind too. And if you were watching this interaction, would you be convinced?
I'd say no,
Why is that?
because how do I know that the two of you beforehand didn't collaborate with each other and decide, oh, I'm gonna first switch the balls, then not, and then not again, and decide on the sequence of events beforehand?
Exactly. Jazzy and I could have totally been colluding. We could have been planning this all along. I might not even be colorblind. Like, who knows? So a third party is never going to find out any information about these balls, or they're not going to find out any other information. Additionally, the most important part is that I never found out anything else other than that the balls are differently colored. Like, yes, I'm colorblind, but she never told me what color the balls are. Like, that doesn't matter. I just found out and confirmed that they are differently colored. So that, go ahead.
So in this case, Jazzy is the prover, you're the verifier?
Yes, Jazzy was proving to me that she knew the balls were different colors. Yes. Okay. So that was just kind of an example for some intuition. Thanks, Becky. Now we're going to move on to kind of just an industry standard example, which is the Alibaba cave. It's the same idea, and I might reference that ball example just to keep things consistent. But to start, we have this fun little cave that was created, and inside the cave, there's a locked door. It'll open from both sides, but you need a secret password to open it. Peggy, the person in purple, claims that she knows the secret password to open this door. Victor is in green. Victor, in this case, is going to be the verifier, and Peggy is the prover. So Victor doesn't trust that Peggy's telling the truth. Why would he? He doesn't know her. And Peggy doesn't trust Victor with the secret. What's the point of knowing the secret password if you're just going to tell everybody? So they're going to design a zero-knowledge interactive protocol so that Peggy can prove to Victor that she knows his password without Victor learning anything else about the password. So the first step of this is we're going to get that commitment that we talked about earlier. So Peggy is going to go in the cave and randomly commit to either path A or B. And then Victor does not see this. He is waiting outside. So he is not, this is a secret commitment. And then once Peggy commits to her side, she can't change it. So Victor is going to come in and be now blocking the middle. So he's then going to call out a challenge. This is what makes it interactive. He calls out the path that he wants her to exit from. A side note, if she didn't know the password and she went down path B and he called A, she would have to go out path B. That would be embarrassing. He would find out she was lying, and we're done. But because she knows the secret password, she can exit through path A like Victor wanted her to. And that is her response. So if this process is repeated, Victor will always be convinced by Peggy, because similar to the way that Jazzy was always able to tell if I flipped the balls or not, Peggy will always be able to come out of the correct side that Victor calls. If she didn't know the password though, and you repeated this process, say 20 or 30 times, her odds of getting it are roughly 1 in a million, basically none. She would have to be the luckiest person on the planet. It would just be negligible. And then another note, if at any point Peggy gets a single answer wrong, abort mission. She was lying. You have to get it right every single time. Even if it's 99 out of 100, it's not enough. You have to get it right 100 times out of 100. So just like I talked about the properties of interactive protocols, I'm going to talk about the properties of zero-knowledge protocols or proofs. So similarly to interactive protocols, zero-knowledge proofs have completeness. If the statement is true, the verifier will always be convinced by the prover. In the cave example, if Peggy knows the password, Victor will always be convinced because she will always come out the correct side. In our colored ball example, I as the verifier will always be convinced because Jazzy could tell me when I flipped the balls every single time. And then the second property is soundness. If the statement is false, no dishonest prover can convince the verifier that it's true. So if Peggy didn't know the password, she would not be able to convince Victor, except with some very, very small possibility. If we ran the protocol many times, Jazzy would probably have gotten one wrong if she was just having to guess when I switched the balls or not. It's also worth noting that completeness and soundness are converses of each other. Just fun fact. And then zero knowledge is the new property of these proofs. And zero knowledge is saying that the prover's secret is never revealed to the verifier, and no third-party observer would be convinced that the statement is true. So nobody outside of this proof protocol would be convinced. So in our cave example, Victor never finds out the password. He doesn't need to. Peggy has proved to him that she knows it without him finding out what it is. And similarly, if someone was watching this interaction, they would not be convinced because Peggy and Victor could be colluding. They could have just agreed on a certain pattern of A's and B's. Similar to the fact that Kyle pointed out, Jazzy and I could have agreed on when I'm going to switch the balls or not. So now, as promised, I'm going to bring you back to the Schnorr protocol and talk about the math behind it. So now that we kind of have some intuition on zero knowledge, we can talk about how it actually works in a realistic scenario. So we have the same protocol pulled up. A reminder that the goal is to prove knowledge of some x such that y equals g to the x. At the beginning of the proof, the verifier only knows g and y. Those are public values. The verifier does not know x, only the prover knows that. But at the beginning, the verifier knows public values g and y. After the commitment is sent, now the verifier knows g, y, and r. Once they pick a challenge, of course, the verifier would know the challenge that they sent, so they also know c. And then once they receive the response, the verifier also now knows z. It is also worth noting, though, that while they do know the value of z, they do not know what t or x are, even though they are part of z. Those values are not actually revealed to the verifier. So then the way that the math works is that you confirm if and only if g to the z is r, y to the c. The computation that the verifier computes, given this response z, the verifier computes g to the z is g to the t plus xc, which is g to the t times g to the xc. Given that, based on our commitment, g to the t is r, which is known by the verifier, and given our original condition that y equals g to the x, we can substitute in y for g to the x. So now we have g to the z, in which the verifier knows z, but we have that t plus xc condition in terms of values that the verifier knows. So he can actually compute that and do a check. So if that checks out, we're good. The prover did actually know what they're talking about. So over the summer, most of our research was dedicated to applying these concepts to matrices and the products of matrices. So like I said, it was computationally difficult to find an x such that y equals g to the x. It's also very difficult to pull out matrices A and B such that C is the product of these two matrices. If I sent you a matrix C, it would not be easy for you to figure out what two matrices I multiplied to get that resulting matrix. So with this idea, we can create a zero-knowledge interactive protocol to verify that the prover knows this product without the verifier being informed of A and B. So the way that we do this is, in general, we're splitting the matrix and folding it in half. So we do this also recursively. So we start with a little diagram. One of the people in our group created this. We split the matrix, fold it in half, and then we have a new matrix, and then we do it again. And we keep going until we have the desired size, and the dimensions just keep getting smaller. However, the resulting matrix still satisfies our initial commitments. So while the size is getting smaller, we're not changing what it is committing to. So, like I said, I was going to come back to the relations. This is the relation for our algorithm that we created for this matrix product. So you can see in the top row, those are all of our public values. We have public values G, H, and U. Those are all matrices. And then in the private values, we have matrices A and B. So the predicate on the right-hand side, so that is our commitment. That is what we end up committing to in the protocol, is P. And similar to how we do it in the Schnorr protocol, we're raising a public value to the power of a private value. And that is computationally hard to get that back. So these protocols are a little bit complicated. So I'm just going to kind of show you a sneak peek of what it looks like. So this one on the left, that is the full protocol for our matrix product. Inside of it, there are 6 sub-protocols. There are pi 1, 2, and 3, and lambda 1, 2, and 3. But you can see similar to the same as the relation that I just showed you. The inputs are our public values and our private values. And then our outputs are just 0 and 1 because the verifier either approves or says, no, they were lying. So a 1 means that it all checks out. The prover did in fact have the information, or a 0 means that they did not and were lying. So that is the full matrix protocol with the sub-protocols in it. And then the one on the right is our final sub-protocol. So that's lambda 3, and that is once we've gotten down to singular group elements from our matrix folding. So we've taken these n by n matrices, and we've been folding the rows, we've been folding the columns, and we've gotten them down to singular group elements. And so we're gonna send the same commitments. We're gonna get a challenge, send some responses, and then the verifier has a final check. And once that checks out, we're good. The protocol is finished. And we've successfully proven that the prover did know the matrices A and B such that they satisfy the product. All right, so while that was the bulk of our research, there are a lot of really fun applications of zero knowledge in the real world. So the first one's blockchain. In a lot of cryptocurrencies, they use these public blockchains like Bitcoin and Ethereum use it. So they're very public. All of your information is out there. There's not a lot of hiding it. And so zero knowledge proofs can be used to verify these transactions. And they can also be used to add a level of anonymity. So if you don't want your name going out there that you transferred 600 billion Bitcoin, you don't want your name out there saying you did that, you can use a zero knowledge proof. The next way that this is used is in finance. So let's just say I'm applying for a mortgage. I want to prove to my bank that I make a salary in a permissible income bracket without disclosing the actual value of my income. So I can prove to my bank, I can say, hey, you need me to be in this range for my mortgage. I'm there, but I'm never actually disclosing what the actual value is. And then another really fun one is anonymous voting. So the way you would do it is that voting, all of the votes would go on a blockchain, and you would use zero knowledge proofs so that the voters can verify their eligibility by saying like, yes, I am eligible to vote, but they don't have to share anything else about themselves. So their name doesn't go on there, nothing about their social security number, nothing like that, but they can verify their eligibility. And then after the voting takes place, they can confirm that their vote was in fact received and counted, and it does not involve a third party, which is one of the important parts of zero knowledge. Those are some fun applications.
You say more about the findings? How do you prove to a bank without telling them I will wait to know?
That's a great question. It was a little bit outside the scope of the research that we did. I just know that it is an application that you can do it. I'm not sure exactly about the way that the protocols work.
So much documents you should do it.
Yes, hopefully in the near future, we will all know, and that would be great. But for now, that's a little bit outside of my scope, but yes, it is a very cool application. So yeah, thank you all for coming. I really appreciate it.
Anybody have any questions for?
Yes.
Can you go back to the protocol outline?
Yeah, sure.
There's one that you didn't, are you?
This one?
Back a couple, yeah, right there.
Yeah, sure.
Let's see, so this is G to the power of A. How do we define this matrix power?
That was a really great question. I might have to think about that and get back to you.
No worries.
Sorry.
Anybody else?
Yes.
Did you have fun?
Yes. I did have fun. It was a great time. I met a lot of really cool people, and I learned a lot.
Is it possible for the verifier to learn some knowledge based off, like, so they do the check 30 times and then all 30 times they're like, okay, they got it right. So you can, the verifier then can take knowledge from that and be like, okay, I think they're right. And so then if I look at their answers, I know that they can't get the complete knowledge, but they can get partial knowledge of the information.
Yes, so there is some situations, especially in our earlier examples, those can be if you have a certain amount of rounds that you go through, you might be able to piece out some knowledge, but in practical purposes and what we actually use for zero knowledge, you're not able to actually pull out any other knowledge. It's completely zero, so you gain nothing other than the fact that they know it.
Are you assuming that the verifier randomly switches or that they could choose to intently switch in order to gain maximum knowledge?
The idea is that the verifier is using a random challenge.
Is it always necessary to work over a prime field, or can you pick some other structure to work over?
I'm pretty sure you need a prime field. I'm fairly confident in that one. I have not taken algebra. This was one of the things that they told me to trust me on this,
Okay.
but I'm fairly confident that I abstract algebra. I've taken regular algebra. I'm pretty sure you do need a prime field.
Okay, well, let's thank our speaker again. And on your way out, there's still, I think there's still some more pizza. If there's not, sorry, but feel free to help yourself to whatever's left. Thank you all for coming.